I'm Bill Cooper. I'm a geologist with Imreys, as mentioned. I'm delivering this talk today on the China clay operations in Cornwall by my company Imreys. This is just a quick overview of what I'll be talking about today. So, an introduction to myself, though Mark's pretty much covered it. An introduction to Imreys, who we are, what we do. A brief history of China clay production in the UK. Imreys' current operations as they are now, covering the mining and refining processes, moving on to geological modelling and mine optimisation that we do here, and finally restoration and rehabilitation once mining has ceased, and then questions and at the end. So this is me. I'm an exploration and resource geologist based in Northwest Europe. I'm part of the mineral resource planning team. We provide support to sites across Northwest Europe for various projects. So in my team there's resource geologists, mine engineers, geotechnical engineers, and we're basically like a semi-consulting arm of Imreys. So I'm attached to a site in Cornwall. I work on other projects in Europe. My background, I'm a School of Mine graduate from Cornwall. Bachelor's degree in applied geology, and I did a master's degree in mining geology after that. I've been a member of IMMM since last year. Previous to that, I was a member of the Australian Institute of Geologists. I've been with Imreys just over 2 years. Before that, I've been exploration and mine geologist in the eastern goldfields of Western Australia. I did that for a number of years, mostly in narrow vein gold. I returned back to the UK in 2012, where I was a consultant for a consultancy in Horsham in Sussex for 6 years. That was mostly resource and mine geology consulting projects in Europe, Eastern Europe mainly, and North Africa. After that, did some exploration in Western states, in Nevada. Difficult during COVID, but I tried my best. And then, so all my background up until me joining Imreys has basically been metals, namely gold and a bit of copper and stuff like that. So this is my first introduction to industrial minerals, and it's very interesting. So I was going to talk about Imreys for a while. So Imreys are a world leader in mineral-based specialities. We offer high value-added solutions to many different industries, ranging from process manufacturing to consumer goods. We are a global leader of these solutions. We contribute essential properties to customers' products and their performance, including heat resistance, hardness, conductivity, opacity, durability, purity, lightness, filtration, absorption, and water repellency. We meet ambitious targets to develop responsibly, focusing on people, the environment, business conduct, and corporate governance. Where we operate, we truly are global. We operate in 50 countries, approximately 230 industrial sites, so every single continent except Antarctica. Half of our revenue comes from Europe, Middle East and Africa, so the green EMEA zone there, and then 30% from the Americas, and probably 20% of our revenue from Asia Pacific. We serve more than 15,000 customers in 140 countries, close to 16,500 employees globally. In Cornwall, we employ just over 1,000. We are one of Cornwall's largest employers. Even though that workforce has shrunk considerably in the last number of years, we are still a major employer. We generated over nearly €4.5 billion in revenue on an annual basis. The UK is the third largest producer of kaolin after Brazil and the USA. We're a primary kaolin deposit in Cornwall. Brazil and Georgia in the US are secondary kaolin deposits, so we are the largest primary kaolin producer in the world. This is our portfolio. So we deliver value-added solutions that are formulated to meet the technical specifications of each customer. Our portfolio is balanced across the various regions, and we supply a wide range of customers across many different industries. So we provide functional additives. This only account for a minor share of the finished product manufacturing cost. E.g. talc improves the rigidity of polymers used in the automotive industry. Calcium carbonate, which makes plastic films breathable for use in food packaging. Mineral components, the second category, is essential constituents in the formulation of customers' products. So zirconia in combustion engine management systems and fused alumina in industrial abrasives. The third category there is process enablers, such as diatomaceous earth, which is a filtration mineral. So lots of different industries covered, lots of products. Within these industries, we're basically split into two broad groups. So the broad group number one is performance minerals, which is the section that I'm associated with. So things like plastics, rubbers, paints, paper and board, ceramics, filtration, and mobile energy. Performance minerals are minerals used as functional additives. And most of our performance minerals customers tend to be regional and are supplied by local plants with their own mines in close proximity. The second segment, high temperature materials and solutions. So we've got things like andalusite in northern France. They're supplied to factory makers who formulate cement, protects furnaces against high temperatures. Fused aluminium products used by manufacturers of abrasive products who manufacture high performance abrasive products like grinding wheels. Another mineral in the high temperature material segment is bentonite, which is used in foundry molds. So that's Imreys. If we focus on UK kaolin in Cornwall, it's a nice snowy scene for you. That's probably taken last week. So the history of China clay, as Mark mentioned, it's quite long and storied. So we've been mining China clay in Cornwall for about 275 years now. Originally discovered by a chap called William Cookworthy in 1746. He was a Quaker chemist from Plymouth. He discovered China clay at Dragonian Hill, which is near Helston in western Cornwall. He discovered that it was a secret ingredient of fine Chinese porcelain. 2 years later, he discovered China clay in the St Austell area, and that's when the industry really took off. By the early 20th century, Cornish kaolin was dominating world porcelain production. So the first 130 years of production in Cornwall were dominated by the ceramic industry. By the 1830s, further markets emerged, with paper market coming to dominate. By the end of the 20th century, a company called ECC International, which some of the older people here may have heard of, they were a FTSE 100 company listed in London. They were the world's largest producer of kaolin at the time, at the end of the 20th century. They were producing 3 million tonnes of clay per year from Cornwall, employed over 3,000 people in Cornwall, and 80% of the product produced at the end of the 20th century was going to the paper industry. Now things have changed since then. Imreys acquired ECC in 1999 or 2000. Following a few other mergers and acquisitions, Imreys is now the sole producer of kaolin in Cornwall. Not the UK, there's another producer mining kaolin in Devon, but in Cornwall we are the sole producer. With the advent of computers, and specifically things like PDFs, the paper market has shrunk significantly in the last 15 years. So we've had to adjust to that market change. So we have shifted away from paper towards performance minerals. So whereas previously kaolin production was focused on high tonnes and low quality. We're now moved towards a lower tonnage, higher quality, higher value mining situation. So historically, you can see there, so very happy people with a hose. Historically, the mining was used basically take a hydraulic hose, point it at the face of clay, and put the clay into the slurry, and then pump it out of the pit. We still do that. We still use hoses. Technology significantly improved since that time. Hoses, that technology is about 150 years old. It started hosing the walls in about 1870, I believe. We still do it, but the techniques changed a fair bit. So what they got up to in the 1800s. So this is what the current operations look like in Cornwall. This is, I think you can see my mouse, but St Austell is down here, just to orientate yourself. We move 12 million tonnes of material a year. Of that 12 million tonnes, it's about 1 million tonnes is ore, China clay. What's known as HCP, which is hydrocyclone product. That's basically our run of mine ore. Picture of the pyramid there. This is in the middle. We've got Carl's Lake complex. That's the largest China clay mine in the world. It was 8 former pits, and they've basically coalesced now into one single operation. This northern pit area is called Little John's, and that is 160 meters deep. So this is the Great Pyramid of Giza. If you drop that in the bottom of the new sink, you would not be able to see the top of it if you stood on the crest. Carl's Lake covers approximately 500 acres. It's got a circumference of about 25 kilometers. It's a very large operation. The other pits that we've got, so 5 active pits. So Carl's Lake's one of them. Will Martin, just to the southeast of it, is another one. And then in the western area, we've got Will Renfrey in the northwest, and then Melba, Virginia, just south of it. The 5th pit is Park and Dillick, and it's tiny, and it's in, this is the village of St Dennis in here. Park and Dillick's in there somewhere. And Park and Dillick's a small little dredging operation that we run. So we now undertake mining using 3 mining methods. So we've got the hydraulic wet mining with the hoses, which I'll talk about more in a bit. There's also a dry mining method, which is basically newer technology, and then we've got the dredging operation in Park and Dillick. So that's the 3 mining methods. So dry mining, hydraulic wet mining, and dredging. It's called dry mining. It's a misnomer, really. It's just slightly drier than the wet mining technique. So the dry mining plant is basically an all-in-one processing plant. It's based in Melba Pit, which is the southwesterly most southwesterly of our pits. It's fed by a front-end excavator, such as one shown here in the wet mining picture. We've got a series of stockpiles up on the surface, and he just loads the dry mining plant. There's a grizzly and a hopper here. It's got a jaw crusher, set of screens, washing facilities, and basically it's an all-in-one processing. Everything that we do in wet mining is just being shrunk into a neat little box. That dry mining plant was installed in 2007, the cost of a few £1 million. It was a significant investment. It's very efficient compared to the wet mining process that we do in the central area pits, Carl's Lake and Will Martin, and Will Renfrey as well. And it allows you, because it's fed from stockpiles, it allows you to blend products. So it's very good. We are currently in the midst of planning to install an extra dry mining plant in the central area to replace the wet mining that we do. So that once that is installed, there will no longer be any hydraulic or wet mining taking place, so that historical method is going to disappear in the next few years. The bulk, so moving on to wet mining, the bulk of our mineral is still produced by this technique. It's about 60% of the clay that we produce in Cornwall is through wet mining. The bulk of it, as you can see here, comes from Carslake, about 330,000 tonnes a year, and then 150,000, roughly 150,000 tonne from Will Rent-Free, 150,000 tonne from Will Martin. I'll talk about wet mining more in the next few slides. The dredging operation, so Parkendillock Pit, as I say, near St Denis, is an X. It's basically a mica impound, and we've got a small dredger that sits on top of that pond. He produces 2% of our product, 20,000 tonnes a year. So a minor operation, but he's recycling former clay waste. So that's a positive thing. We're removing some old waste material. It's low cost and we get a lot of good quality clay out of it. So even though it doesn't produce a lot, the margins on the dredger are quite good. So the wet mining, hydraulic mining technique, historically, the hose was taken to the face. That had advantages for material movement and things like that, but taking the hose to the face doesn't allow you to control the qualities very well. So when we were producing the materials in the 19 and 1900s, it was less of an issue. It was all basically going for low-grade filler for paper. Nowadays, as we're moving towards high-value products, we need a lot more control in the pit. Basically, we produce there's at least 6 different grades from each. We've got 6 different grades across the operations, which produce up to 50 products ultimately. So what we do now is more traditional mining, what you'd consider in a normal open pit. So we cut and carry. The bench is blasted, some sort of, where it's particularly clay rich, just free dug by a 150 ton backhoe. Fill 40 ton trucks, usually articulated dump trucks, and they cart the ore to a set wash point. So each pit has a series of wash points, or stopes as we know them, which is confusing if you've ever worked underground. These wash points, the hose is fixed in place on the monitor, and the ore is dumped basically over the top of the stockpile and is washed by the monitor. So each stope, and Carslake has, I think, 3 wash points. Each stope has its own quality, so we can control the feed that way. Once the face is washed, so the clay slowly goes into solution, it's then transported, it runs by gravity down to the bottom of the pit, known as the sink, and that's where we start doing some processing. So here in the image you can see a set of bucket wheels. These are basically screen sand classifiers. So the slowly runs down to the sink. The gravel pump is then used to pump them into these bucket wheels. These wheels rotate slowly. There's a mesh screen on each bucket, and it screens out the sand, and coarse material ranges in size from like 1.5 to 5 millimeters. That sand is then stockpiled and hauled away. The fine slurry is then pumped to the next process, which are the hydrocyclones. So each pit where we're wet mining has a bank of hydrocyclones. This takes a slurry, they're basically cyclones, so it spins at a very high speed. They're cut to about 50 microns, so we are in the realm of clay, but it's still, for us, 50 microns is still very coarse. That 50 micron product is then pumped to the refiners, and we've got 3 refiners in the UK on the platform. That product is pumped to the refiners for further processing. So this is simply a simplified process route. So we've got the wet mining or dry mining up here. The slurry goes into the screen sand classifier bucket wheel. We've got coarse waste stockpile, which is the sand. The fine slurry goes to the hydrocyclones, which then goes to the refiners. The refiners are basically mineral processing plants, which are designed to remove the smaller size waste particles. So we're below the 50 micron cut now. Refiners can also add value by a variety of processes designed to engineer size and shape of the product, together with bleaching the clay if need be to improve its whiteness. Refiners further reduce the particle size using things such as centrifuges. Particle size is reduced to 20 microns and below. Using centrifuges, magnets and sand grinders. From the refiner, the material is pumped again to a secondary processing site, which adds further value in a variety of ways before the final product is sold. After the secondary processing, we go to a drying stage. So the dryers first convert the liquid slurry to a solid material through a filter press. Filter presses produce a product which is generally about 25% moisture. After that, it's put into an oven or thermal dryer, and that 25% moisture is brought down to about 10%. That 10% moisture product is pelletized or noodled into noodles about 6 centimeters long and a couple of centimeters wide. And those noodles are then taken by either lorry or rail to UK markets or to a dedicated dock facility in Foy, just southeast of St Austell, where it's shipped to foreign markets. And I believe about 70% of our product is exported. So we are producing a lot of clay and we are producing a lot of money for the Cornish economy. Moving on to the geology. Where's it gone? On the next one? Yeah. So what actually is kind of clever, we've been talking about this slurry. Our ore is basically a mixture of kaolinite and fine quartz, mica and feldspar, the usual minerals that you find in granite, which is the host rock that we are processing. So kaolinite is formed by hydrothermal or weathering alteration of felsic rocks, such as granites, and it's formed by acid hydrolysis of aluminosilicates. So basically, there's a lot of feldspar in granite. It's attacked by acid hydrothermal fluids, and it's converted that feldspar. So we've got orthoclase here, which is potassic feldspar, and albite, which is sodic feldspar. Those are attacked by water, H2O, to form kaolinite and waste silica, and either potassium if it's orthoclase or sodium, calcium if it's plagioclase feldspar. So kaolinite is a fairly simple aluminosilicate. It's got high brightness and whiteness. It's got good coating power. It's non-abrasive. It's refractory, so it remains white after firing, which is very important if you're going to make nice white bathroom tiles. It's got weak conductivity, and it's hydrophilic, so it's easily dispersed in water. So it's got some very useful properties which allow it to be used in a variety of products, as mentioned before. Come on, why am I doing that way? Yeah. So our kaolin product isn't 100% kaolinite. So if we look at the 50 micron, it's a mixture of minerals, as I said before, usually kaolinite, feldspar, quartz and mica. And it's very much, the chemistry of the product is very much driven by the particle size. So at the 50 micron stage, which is the ex-pit product, you can see the product is still very much dominated by quartz and feldspar, quartz and mica, I should say, with maybe only 10% kaolinite. Once we get to the refining stage, 20 microns and below, you'll see that kaolinite content exponentially increase as we lose the mica, quartz and feldspar. Our crude kaolin is typically between 30 and 60% below 2 micron, so extremely fine. Even below 20 micron, we've still got these other minerals in there, quartz, feldspar, etc. Not a lot of titanium. Secondary kaolin deposits like the ones in Brazil and America have significant titanium, which can cause problems. Contains some K2O. That's an important. K2O is an important, not element. It's an important variable for us. It affects certain products certain ways, so it can make the kaolin quite brittle. So for certain applications, we want a really low K2O. So yeah, other associated minerals strongly influence the properties of the feeds and final products. For example, this top graph shows the typical mineralogy of the ex-pit product from each of our pits. So we've got Melba, Will Martin, Will Renfrey and Carslake, and you can see the underlying geology really drives what the makeup of the kaolin is that comes out of the pit. So we've got different granites on the platform, which I'll talk about in a second. Each product, each pit, quite different. So you can see different amounts of kaolinite. Same minerals again. So we've got mica in green, quartz in purple, feldspar, montmorillonite, which is another aluminosilicate clay mineral, and tourmaline as well. And then from the ex-pit products into the final products, still these are all mineral makeups from a number of our final products. And you can see, again, depending on customer requirements and a few other things, our final products have a distinct mineralogy as well. And some of them only contain maybe 60-70% kaolinite. And we've got micas in there and feldspar. So the processes in the refining and secondary processing stage, we can concentrate or get rid of some of these mineralogy fractions to bring the desired properties to the final product that the customer requires. Moving on to the geology. So for those not familiar with the geology of Cornwall, it's very old. Formed during the Briscan orogeny. We've got basement rocks of Devonian age, which are I think 350 million years old. But what's important is the Cornubian batholith, which is a large granitic body that underlies pretty much the whole of southwest England. It's exposed on surface in 6 major plutons. So we've got Land End and the Isle of Scilly in the far west, Carmen Ellis around Camborne and Redruth, which is famous for its tin and copper deposits. Tregonin Hill, where Cook Webby first discovered china clay, that's that little pluton down here near Penzance. And then as we move east, the St Austell Pluton, Bodmin Moor, and then finally Dartmoor. Each of the plutons has produced china clay in its past, with the exception potentially of Carmen Ellis. The only areas currently now producing china clay are the St Austell granite, we're in Cornwall, and then we've got some operations over the border in Devon, the southwest corner of Dartmoor near Plimpton down here. But focusing on the St Austell granite, it's not a single granitic body. There's quite a distinct makeup. So it's actually 5 different granite types that have kind of been mapped across the entire batholith. Within St Austell, we only see really, 2 of those granite types. So a tourmaline granite and a topaz granite. For those that attended Andrew Smith's talk last month on the Gunheath British Lithium project, that's in the topaz granite over here on Henswood Downs. That's young, that's postulated to be younger than every other granite in the St Austell area. So all these lithium microgranites and tourmaline granites, these are all basically fractionation series. So it's the same melt, but it's just got different fractions. The G5 granite, the topaz granite, which is now being explored for lithium, is postulated to be younger, and it's accepted to be another melt and another a separate intrusion that's intruded into the former tourmaline granites. So I've been talking about primary and secondary kaolin deposits. This little infographic show is designed to show you what that means. So primary deposits are hydrothermal weathering alteration of granite in situ, such as Cornwall and Devon. Secondary deposits are transported and deposits of primary kaolin and weather materials under tropical conditions, such as ball clay deposits we've got in Devon, deposits in Georgia on the eastern coast of the States, and Brazil. So there's your granite in pink, got a bit of plutonic uplift, some fracturing, which is very important for getting the fluids into the granite to decompose the feldspars and create the kaolinite. We've got weathering from the surface. We've also got hydrothermal weathering coming up from the ground, and then that's what we're left with. So we've got primary kaolin in the granite, usually hosted by the fractures, and then running off that we've got the secondary kaolinite deposits, usually downhill and downstream. So the ball clay deposits in Devon, for example, around Bovey Tracy, were formed by runoff from the Cornubian batholith, so Dartmoor and everywhere else. So what do our primary kaolin deposits look like in cross section? They are basically funnel shaped. So we've got within the granite veins and fractures. Those veins and fractures have focused fluid flow, and this is where we see the colonisation. So it's a gradational. We've got gradational decomposition. So very close to the veins. This black line would be a quartz tourmaline vein, for example. That's where the strongest colonisation is, and as you move away from that vein, the colonisation gets weaker and weaker. So grade 5 is over here. This is the strongest degree of decomposition and colonisation that we see on the platform. That's all feldspars destroyed. Some micas get in extreme colonisation zones. Some micas are destroyed as well. And then as you move grade 4, grade 3, grade 2, decomposition gets less and less, and then basically grade 2 is as new as damn it fresh granite. This is important because we get different amounts of clay from each decomposition grade. So yield is a very important factor in primary kaolin deposits, and yield is the amount of clay or HCP we get out of each ton of material. So from a grade 5 area, we would expect maybe 35–40% yield. So 1 ton of rock would produce 350 kilos of clay. When we get down to grade 3, we're looking at maybe 6 to 10% clay out of a ton of rock, so significant differences in amount of product that we get from each decomposition grade, and this is the area that we focus our geological modelling on and estimation. Historically, that's what would have been mined in the past, so I would say geological control in the 1800s and maybe even 1900s was been fairly limited. This superficial blanket of clay would have been pretty much G5, fully colonised everywhere. So clay as far as the eye could see. Not much need to worry about differentiation and chasing veins. That situation after 250 years of mining is no longer the case. So our pits, we're basically now mining the guts of the guts and the roots of the deposits. So we're now basically in a situation where we're mining loads of veins of clay in a corridor, which requires much more geological input. So we've got mine geologists now dedicated to in each pit, doing grade control in pit to help identify these clay corridors and mine the right stuff, basically. Yeah, again, so this is just these 4 different grades of colonisation that we see in the UK. So grade 2 is basically fresh granite. You can't break it by hand. Grade 3, the plagioclase tends to alter first, so they tend to go to kaolinite first, and then the orthoclase starting to alter, but not a lot. Grade 4, basically we're getting more orthoclase destruction. The rock is now breakable by hand. And then G5, grade 5, all feldspars are completely gone. It's malleable, so you can pick up this lump of clay. It's usually quite wet, and you can shape it by hand, even with the bits of quartz and tourmaline that are still in it. So, we're doing for time. As we are now in basically a proper mining scenario, I suppose, for want of a better term, we are doing proper geological work. So we drill and estimate these deposits as you would for, say, like you would a metal deposit. So start off with drilling data, geological mapping, build a nice geological model, estimate certain qualities into that model. So I'll talk about that in a little while. And then that block model is then given to a mine engineer who runs optimization processes and scheduling. So we have moved. This is quite a new, I would say this is a fairly recent development. Historically, maybe 20 years ago, the geological and mine engineering input was not as sophisticated, I would say. So we're trying to move with the times, building 3D geological models in appropriate software, doing optimizations and scheduling, just trying to be a bit more professional about the whole value chain, really. Right. Oh, excuse me. So the geological model is built on two main sources of data: geological mapping. So we map for colonisation grade. So these colours, green's basically fresh rock, so grade 2, grading into yellow, which is G3, grade 3, orange, which is grade 4, and then red, which is grade 5. So as I said before, the grade is very crucial to the yield that we get, so it's very important to our bottom line. So we map using tablets in the field, digitize them in GIS back in the office, and then bring those digitized points into a modeling software for integration into our geological model. Drill data, we've been drilling on the platform for a long time, since the 1950s. Usually you can see this timeline here in the bottom. It's usually quite campaign driven, so we have spikes where we drill heavily and then not drill at all. So historically, in the 50s and 60s, we were drilling slurry holes, and slurry holes are basically rotary drilling using a water flush tricone bit, which produced slurry and chip-ins. That then moved on to coring in the 1970s. So intermittent coring is still a slurry hole, but every so often we take a core sample for testing and logging. As we move into the 1980s, coring is becoming more and more regular. Up until 1990, ECC were running up to 9 rigs in Cornwall, usually coring rigs. That dropped off until the early 2000s. I think there was no rigs on site then, maybe 1 or 2. We trialled reverse circulation in the early 2000s. Reverse circulation produces chips like the slurry holes does. It's called reverse circulation because the drill chips travel up the inside of the drill string, therefore not getting contaminated on the wall of the hole as they come out of the hole. Very popular in Australia. If anyone works in Australia, a lot of reverse circulation drilling out there. It's cheaper and quicker than diamond coring. We found here that it wasn't, due to the nature of the rock that they were drilling. It doesn't like clay very much. They get clogged up quite a lot. So we didn't get the time and cost savings that you'd expect. So it was dropped basically. A bit of rotary air blast. So that's the chips come out on the outside of the hole, so you get contamination. We don't use those in modelling. We grade control usually. In 2011, we had a sonic drilling campaign. So sonic drilling's quite a new, interesting drilling technique. So it's a coring method, but there's a sonic head attached to the head of the drill, which imparts a resonance into the drill string at about 150 hertz. That allows you, in soft formations, it really increases penetration rate and recovery. And I'll talk about the sonic program in the next slide, but we were getting excellent recovery and penetration rates, but we had an issue with the sample, so I'll talk about that in a second. But we've gone from that. We're now drilling since 2015 large diamond drill core. So GeoBore S is 100mm diameter core, which is significant. We've now got our own drill rig, the GeoBore, on the platform, which allows us to be quite flexible compared to the campaigns of the past with using contractors, such as the campaign we had in 2017. So going back to the sonic drilling, as I say, we've excellent recoveries and penetration. However, upon sampling and assaying of the core, it was determined that the yields, the clay content that was coming out of these samples was anomalously high. So following some twin studies against the diamond core, really high yields, it seems that the sonic resonance was in areas of semiconization. So we've got this grade 3, grade 4. It was basically the feldspars that were still in the granite were being broken up, and it was basically creating fines. So these feldspars would break up. They'd end up in the refined assay product. So it was basically giving us a lot more clay than was there in reality. The other problem with incorporating feldspar is it tends to have a lot of K2O in it, potassium. We don't like, a lot of our customers don't like potassium. K2O tends to say it affects the rheology of the clay. So not only were these sonic holes overstating the clay content, they were overstating potash K2O content as well. That was quite interesting. So yeah, with the geological modelling, there's nothing really revolutionary that we're doing on the platform. We're incorporating mapping data and drill data into a geological model using 3D software. We tend to use an implicit modelling software. We model the lithologies, so it's usually just granite solid, and then we've got overburden, tip. Sometimes we've got elvins, which are basically fine-grained felsic intrusives. And then within the granite solid, we then model the decomposition grade. So you can see in this bottom image, we've got grade 5, and you can see the gradational nature of the decomposition. So we've got grade 5 in the middle. As you move away from the vein that would be in there, you go into grade 4 and then grade 3. So I say nothing revolutionary really. We've got a geological model, make a block model. We do some stats, as visual geologists are partial to. Estimate using ordinary kriging. I'm not. The technical details are going to be very light in this talk. Estimate using ordinary kriging, and then we create our block model. That block model then goes to our mine engineer, who undertakes pit optimization. So this is quite a new thing to do on the platform. With the pit optimization, I would say the most complex things are the amount of products that we produce and could produce. We've got lots of different cutoffs for lots of different things. So on the estimation side, we estimate chemical and physical properties of the kaolin. So chemical properties such as iron and K2O. Iron is important because it makes the clay yellow. No one wants a yellow bathroom, so iron is very important. K2O, as I said before, you can make the product brittle, which is a problem. Physical properties that we estimate are flowability, so basically viscosity, particle size distribution, and brightness, so whiteness. So we tend to have lots of products, lots of variables, lots of cutoffs, and the other constraint, I suppose, is infrastructure. So we've been around a long time. There's lots of infrastructure around. We've got pipelines that run from the pits to the refiners. We've got just hundreds of kilometers of pipelines around. We've got old tips. We've got refining sites, roads, all sorts. So the pit optimization process has its challenges, but it's very important. After optimization, mine planning and scheduling. I'm not mine engineer, I'm not going to talk about it too much, but we basically create a load of scenarios and do a detailed mine plan for the next, short, medium and long-term mine planning, scheduling. We've recently acquired a drone, so we've got quite a lot of ground to cover. As I say, our operations cover about 50, 70 square kilometres. So our survey department have worked very hard. We've got a drone which now, or 2 drones, I should say, which allow us to quickly undertake topographic surveys across the platform. It's very useful for reconciliation, design implementation, monitoring of pit walls, etc., etc., etc. So that's good. So that's the current operations. I suppose all good things must come to an end. We've got many years of mine life left in Cornwall. We're certainly closer to the end of trying to claim Cornwall than we are to the start. I can't put an exact figure on how long we've got left, but we're running into the decades, I'm sure. Given that we are operating multiple pits with multiple timelines, closure and rehabilitation plans are a fundamental part of operations in Cornwall. It's an exercise in land management. The current challenge is to identify opportunities for solid and residue waste storage. Given that we've got these lithium projects taken off as well, that challenge is even more increased now. So there's even more strain and pressure on existing pits and tips for waste storage. We try to minimise the waste that we produce. So, as I said before, we move about 12 million tonnes of material a year. Only 1 million tonnes of that is clay product. So that's a significant amount of material that needs to be found home. So we do tip on the surface, and once those tips are finished, they are hydroseeded and graded. We try to recycle as much as we can. So we've got aggregate partners at each of our operations who take some of our waste sand, hard rock, the granite that we produce quite a lot of hard granite in the G2 that needs to be moved. So those aggregate partners take those off us as well. So we recycle where we can. The residual material from the refiners and dryers ends up usually in dedicated storage facilities, mica dams, former pits. So Hendra and Dorothy are taking a lot of residue, for example. And those pits can be remined for clay as well. So say in the case of Park and Dillet, where we've got our dredger, that's a former residual pond that we are now remining for clay. So we are very keen to recycle wherever possible. Imreys is quite keen on green technology. So we've got 4.5 megawatt wind turbines on our land, 8 solar energy farms and 2 small hydro energy schemes. That represents a combined generating green energy potential in excess of 35 megawatts. So this solar farm you see here, this is Kernick mica dams. This is a former mica dam. It's the largest on the platform. Melba Pit is over here. It's now home to a large solar farm. So wind turbines. We've got wind turbines at Carslake and around Gunheath, where the lithium project is. That's taking advantage of its topography. So Hensborough Downs, which is next to Gunheath Pit, is one of the highest points in Cornwall. So perfect for wind turbine. It's always blowy up there. We're currently investigating further wind, solar, and hydro opportunities across the UK. But yeah, for now, we've got lots of renewable sites on the platform, which is really good to see. It could be better. Our carbon footprint, our thermal dryers, for example, we've got 3 drying sites. They're all gas fired. We're in the process of converting those gas plants to something a bit greener. So that is happening, will be happening over the next few years. So once our dryers are converted from natural gas, our carbon footprint will be much reduced, which is really great. Finally, so when mining does cease, we're going to have quite a lot of land left over. So one of the current projects is West Carclay's Garden Village. So this is in the old Eastern Area mining area, so not far from the Eden project. It's just north of St Austell. It's about 2.5 miles north of St Austell. It's 350 acres of managed country park. There's going to be a 7 megawatt solar farm built there. 5 lakes in a unique environment. So this sky tip is great for Trevin Tip. If you've ever driven on the main road into St Austell, you'll go past Trevin Tip. This village is going to house about 1,500 houses. They should all have. It's going to be. The aim is for it to be as sustainable as possible. So ground source heat pumps, solar panels on roofs, all this kind of thing. So this is currently being built as we speak. The company has also been involved in rewilding and environmental restoration elsewhere. We own about 5,000. We've got a 5,000 hectare land holding. As part of this ongoing restoration and rewilding project, we've planted over 2 million trees. We've created more than 2,000 hectares of heathland and woodland, such as Carolin Downs, which is very close to where West Carclay's village is being built. Also, Gun Heath Tip is another major restoration project. In addition to that, we've also created and maintained over 40 kilometres of primitive paths. So if you've ever been in the St Austell area, there's what's known as the clay trails, which takes you around former and current operations around Wilmartin and Eastern area. We've rehabilitated over 1,500 acres of land, and that's created new habitats, which has led to the introduction of bees, butterflies, deer, and many species of bird. And that is the end of my presentation. I thank you for your attention, and any questions I will gladly answer them.